Hey, my name's Jonathan Pan, and today I'll be reading No Silver Bullet by Frederick P. Brooks Jr. And starting off um, with the abstract, all software construction involves essential tasks, fashioning the complex conceptual structures that compose the abstract software entity, accidental tasks, representation of the abstract entities in programming languages, and the mapping of these onto machine languages within space and C constraints. Most of the big past gains in software productivity have come from removing artificial barriers that have made accidental tasks inordinately hard, such as severe hardware constraints, awkward programming languages, lack of machine time. How much of what software engineers now do is still devoted to the accidental as opposed to the essential? Unless it is more than nine-tenths of all effort, shrinking all the accidental activity to zero time will not give an order of the magnitude improvement. Therefore, it appears that the time has come to address the essential parts of the software task. Those concerned with fashioning abstract conceptual structures of great complexity. I suggest exploiting the mass market to avoid constructing what can be bought, using rapid prototyping as part of planned iteration and establishing software requirements, growing software organically, adding more and more functions to the system as they are run using tests, identifying and developing the great conceptual designers of the rising generation. Moving into the introduction, of all the monsters who fill the nightmares of our folklore, none terrifying more than werewolves because they transform unexpectedly from the familiar into horrors. For these, we seek bullets of silver, then can magically lay them to rest. So, as I continue, the familiar software project has something of this character, usually innocent and straightforward, but capable of becoming a monster of missed schedules, blown budgets, and flawed products. So we hear desperate cries for a silver bullet, something to do, something to make software costs drop as rapidly as computer hardware costs do. Um, but as we look to the horizon of a decade hence, we see no silver bullet. There's no single development, either technology or management technique, which by itself promises even one order of magnitude improvement in productivity and reliability and simplicity. In this chapter, we shall try to see, but examining both the nature of the software problem and the properties of bullets proposed. Skepticism is not pessimism, however. Although we see no startling breakthroughs and indeed believe such to be inconsistent with the nature of software, many encouraging innovations are underway. And we see here now that like the first step toward the management of disease was replacement of demon theories and humors theories by the germ theory. That very step, the beginning of hope in itself, dashed all hopes of magical solution. It told workers that progress would be made stepwise at great effort and that a persistent, unremitting care would have to be paid to a discipline of cleanliness. So it is with software engineering today. So as I move on in the next section, does it have to be hard? And what are the essential difficulties? So not only are there no silver bullets now in the view, the nature of software makes it unlikely that there will be any no inventions that will do for software productivity, reliability, and simplicity. What electronics, trans, transistors, and large-scale integration did for computer hardware. Could not expect ever to see twofold gains every 2 years now. Um, First, we must observe that the anomaly is not that software progress is so slow, but computer hardware progress is so fast. See, and this is making me think about how like hardware as super important to the power of how fast and how scalable and a software can run. And as I continue to the next line, no other technology since civilization began has seen six orders of magnitude price performance gain in 30 years. And no other technology can one choose to take the gain in either improved performance or in reduced costs. These gain flows from the transformation of computer manufacture from an assembly industry into a process industry. Second, to wait to see what progress we can expect in software technology, let us examine its difficulties. Following Aristotle, I divide them into the essence, the difficulties inherent in the nature of the software, and accidents, those difficulties that today attend its production, but that are non-inherent. The accidents I discuss in the next section. First, let us consider the essence. The essence of a software entity is a construct of interlocking concepts, data sets, relationships among data items, algorithms, and invocation of functions. Its essence is abstract in that the conceptual construct is the same under many different representations. It is nonetheless highly precise and richly detailed. I believe the hard part of building software to be the specification of design and testing of this conceptual construct, not the labor of representing it and testing the fidelity of the representation. We still make syntax errors to be sure, but they are flaws compared to the conceptual errors in most systems. And this is making me think about how it's important to understand what ideas you want when you're creating software. Um, it's not the language that you're using, but rather the concepts you want to gain, the concepts that you want to execute, and which computer language I'm thinking about now is best to help you execute what you desire. Continuing on the next page, this is true. Building software will always be hard. There's inherently no silver bullet. Um, and it's important to consider the properties of complexity, conformity, changeability, and invisibility. So starting off with complexity, software entities are more complex for their size than perhaps any other human construct because no two parts are alike. If they are, we make two similar parts into one. Subroutine open or closed. In this respect, software systems differ profoundly from computers, buildings, or automobiles, which repeated elements abound. Interesting. Yeah, and that makes sense as um, yeah. And digital computers are themselves complex than most things that people build. They have very large numbers of states. This makes conceiving, describing, testing them hard. Software skills, software systems actually have orders of magnitude more states than computers do. Likewise, the scaling up of a software entity is not merely a repetition of the same elements in large size, it is necessarily an increase in the number of different elements. In most cases, the elements interact with each other in some non-linear fashion, and the complexity of the whole increases much more linearly. Complexity of the software is an essential property, not an accidental one. Hence, descriptions of a software entity that abstract away its complexity often abstract its essence. Mathematics and physical sciences make great strides for 3 centuries by constructing simplified models of complex phenomena, deriving properties from the models and verifying those properties experimentally. This worked because the complexities ignored in the models were not essential products of the phenomena. It does not work when the complexities are the essence. Many of the classical problems of developing software products derive from this essential complexity and is nonlinear, increased with size. From the complexity comes the difficulty of communication among team members, which leads to product flaws, cost overruns, schedule delays. From the complexity comes the difficulty of enumerating much less understanding all the possible states of the program, and that from that comes the unreliability. From the complexity of functions comes the difficulty of invoking those functions, which makes programs hard to use. From complexity of structure comes the difficulty extending programs to new functions without creating side effects. From the complexity of structure comes the unvisualized state that constitute security trapdoors. Not only technical problems, but management problems as well as come from the complexity. Complexity makes overview hard, thus impeding conceptual integrity. It makes it hard to find and control all the loose ends, right? It's the tremendous learning and understanding burden that makes personal turnover a disaster. As I reflect that, as software systems become much larger, much more scaled, and it's important that um, teamwork is very paramount, as I'm noticing right here, and that um, definitely that the more complex the system, the more issues are. So making sure that team members are all aligned on how the software system works and how to use that system are very important, I believe, as I'm starting to read this. And moving on to conformity. Software people are not alone in facing complexity. Physics deals with terribly complex objects, even at the fundamental particle level. Physicists labors on, however, in a firm faith that there are unifying principles to be found whether in quarks or in unified field theories. Einstein repeatedly argued that there must be simplified explanations of nature because God is not capricious or arbitrary. No such fate comforts the software engineer. Much of the complexity he must master is arbitrary complexity, forced without rhyme or reason by the human institution and systems to which his interfaces must conform. These differs from interface and from time to time, not only because of necessity, but only because they're designed by different people rather than by God. In many cases, the software must conform because most it has most recently come to the scene. In others, it must conform because it is perceived as the most comfortable. But in all cases, much complexity comes from conformation to other interfaces. This cannot be simplified out by any redesign of the software alone. Interesting. I want to move on to changeability. Software entity is constantly subject to pressures for change. Of course, so are buildings, cars, and computers, but manufactured things are infrequently changed after manufacture. They're superseded by later models or essential changes by are incorporated in later serial number copies of the same basic design. Callbacks to automobiles are rare, are really quite infrequent. Field changes in computers somewhat less so. Both are much less frequent than modifications of field software. Interesting. Yeah, I could see this as like apps constantly are getting updates. Um, and like it's much harder with the hardware component because you need new supplies. Your R&D is much more tough, I think. And especially with software now, you're able to quickly test it. You have an environment that you can easily test these changes, see if you need to implement these new features or not. So this is really interesting. I want to move on as all successful software gets changed. Two processes are at work. Software product is found to be useful. People try in new cases at the edge of or beyond the original domain. The pressures for extended function come chiefly from users who like the basic function and invent new uses for it. Second, successful software also survives beyond the normal life of the machine vehicle for which it is written. If not new computers, then at least new disks, new displays, new printers come along, and the software must be conformed to the new vehicle's opportunity. Short, the software product is embedded in a cultural matrix, applications, users, laws, and machine vehicles. These all change continually, and their change inexorably force change upon the software product. That makes sense as software must adapt with these new hardware products as well in order to still for these products to be advanced. So it's a good relationship that is established. I want to move on to invisibility. Software is invisible and unvisualizable. Geometric abstractions are powerful tools. The floor plan of a building helps both architect and client evaluate spaces, traffic flows, and views. Contradictions become obvious. Omissions can be caught. Scale drawings of mechanical parts and stick figure models of molecules through abstraction serve the same purpose. Geometric reality is captured in a geometric abstraction. Reality software is not inherently embedded in space, hence has no ready geometric representation in the way that LAN has maps, silicon chips have diagrams, computers have connectivity. Schematics, as soon as we attempt to diagram software structure, we find it to constitute not one, but several general directed graphs superposed on one another. Several graphs may represent the flow of control, data, patterns of dependency, time sequence, namespace relationships. These are usually not even planar, much less hierarchical. Indeed, one of the ways of establishing conceptual control over such structure is to force link cutting until one or more graphs becomes hierarchical. Despite a progress in restricting and simplifying structures of software, they remain inherently unvisualizable, thus depriving the mind of some of its most powerful conceptual tools. This lacks not only impedes process design within one mind, it severely hinders communication among minds. Interesting. Um, Want to move on now. Past breakthroughs solve accidental difficulties. Interesting. So, if we examine the three steps in software technology that have been most fruitful in the past, there's a discovery that each attacked a different major difficulty in building software. Accidental, essential, but they have been accidental, not the essential difficulties. Interesting. We also see the natural limits to the extrapolation of such attack. Okay. The most powerful stroke for software productivity, reliability, and simplicity has been the progressive use of high-level languages for programming. Interesting. Most observers credit the development with at least a factor of 5 in productivity and with concomitant gains in reliability, simplicity, and comprehensibility. Okay, interesting. So now I want to read what does a high level language accomplish? So frees a program from much of its accidental complexity. Abstract program consists of conceptual constructs, operations, data types, sequences, and communication. The concrete machine program is concerned with bits, registers, conditions, branch channels. To the extent that the high-level language embodies the constructs wanted in the abstract program avoids all lower ones. It limits the whole level of complexity as never inherent in the program at all. Continuing on, the most high-level language can do is to furnish all the constructs the programmer imagines in the abstract program. To be sure, the level of our sophistication in thinking about data structure, data types, operations is steadily rising, but at an ever decreasing rate, and language development approaches closer and closer to the sophistication of users. Moreover, at some point, the elaboration of a high-level language becomes a burden that increases, not reduces, the intellectual task of a user who rarely uses the esoteric constructs. Interesting. Want to move on to time sharing now. Most observers credit time sharing with major improvement in the productivity of programmers and the quality of their product, although large as that brought by high-level languages, time sharing attacks a distinct different difficulty. Time sharing preserves immediacy, and batch programming means that we inevitably forget the minutiae, if not the very thrust of what we're thinking when we stop programming and call for compilation and execution. This interruption of consciousness is costly in time, for we must refresh. The serious effect may well be the decay of grasp of all that is going on in a complex system. Slow turnaround, like machine language complexity, is an accidental rather than an essential difficulty of the software process. The limits of the contribution of time sharing derive directly. The principle is to shorten system response time as it goes zero. At some point, it passes the three-dimensional noticeability about 100 milliseconds. Beyond that, no benefits of be shifted. Okay. I see. 100 milliseconds is very fast. Wow. Okay. Unified programming environments. Unix and Interlist, the first integrated programming environments, come into widespread use are perceived to have improved productivity by integral factors. Looking at why now, they attack the accidental difficulties of using programs together by providing integrated libraries, unified file formats, and piles and filters. I'm seeing now as a result, conceptual structure that in principle could always call feed and use another one can indeed easily do so in practice. This breakthrough in turn stimulated development of whole tool benches since each new tool can be applied to any programs by using the standard formats. Because of these successes, environments are the subject of much of today's software engineering research. You'll look at their promise and limitations in the next section. Okay. Seems very interesting. I'm excited to see. Um, I want to move on now. Hopes for the silver. Considering the technical developments that are most advanced as potential silver bullets. What problems are addressed? Problems of essence, remainders of accidental difficulties that offer revolutionary advances or incremental ones. So looking at Ada now. Um, I've heard of Ada before. I'm reading now that general purpose high level language of the 80s and that it's not only reflecting evolutionary improvements in language concepts, but features to encourage modern design, modularization concepts. So, um, I moved down as well, like advancing the structure of software systems, is indeed very good. Use for increased MIPS our dollars will buy. Um, Operating systems loudly decried in the 1960s for the memory and cycle costs have proved to be an excellent form of in which to use some of the MIPS and cheap memory bytes of the past hardware surge. Ethernet will not prove to be silver bullet as slaves software productivity monster. It is, after all, just another high-level language. The biggest payoff from such languages come from the first transition. One of those accents have been removed. Once those accents have been removed, the remaining ones are smaller, and the payoff from the removal will surely be less. I see. Predict that from a decade from now, when the effectiveness of ADA is assessed, it will be seen to have a substantial difference, but not because of any particular language feature, nor indeed because of all of them combined. Neither will the new ADA environment prove to be because of the improvements. ADA's greatest contribution will be that switching to occasion trained programs and modern software design techniques. Moving on to object-oriented programming, I think that I got a small introduction in CS1331, so I'm interested to continue to read about this section now. Many students of the art hold out for hope for object-oriented programming and other technical fads of the day, distinguishing I'm among them. Seeing that Mark Sherman of Dartmouth, there's is noting that two separate ideas with abstract data types, hierarchical types, um, also known as classes. Concept of abstract data types and objects types should be defined by name, set of proper values, and a set of proper operations rather than a storage structure. So like private, public. Okay, interesting. I'm reading now with these ADA packages and then hierarchical types such as Simulus 67's class allow the definition of general interfaces that can be further refined by providing subordinate types. These two concepts are orthogonal. There may be hierarchical hierarchies without hiding and hiding without hierarchies. So that's a real advance in the art of building software. Each removes one or more accidental difficulty from the process, allowing the designer to express the essence of his design without having to express large amounts of syntactic material that add no new information context. For both abstract types and hierarchical types, the result is to remove a higher order sort of accidental difficulty and allow a higher order expression of the design. So the complexity, so advances can do no more than to remove all the accidental difficulties from the expression of the design. Complexity of the design itself and attacks make no change whatever in that. Order and magnitude gain can be made by object-oriented programming only if the unnecessary underbrush of type specification remaining today on our programming language is itself responsible for 9/10 of the work. Take a breath. Take a breather now. Many people expect it. Oh, okay, now we want to move into artificial intelligence. So many people expect advances in artificial intelligence to provide the revolutionary breakthrough that will give order of magnitude gains in software, productivity, and quality. I do not to see why we must dissect what is meant by artificial intelligence and then see how it applies. So Parnas has clarified the technological chaos. So two quite difficult, two quite different definitions of AI are in common use today. So computers to solve problems that could only be solved by human intelligence. And then set of specific programming techniques, heuristic or rule-based programming. Human experts are studies to determine what heuristics or rules of thumb they use in solving problems. The program is designed to solve a problem the way that humans seem to solve it. Just sliding meaning. So something can fit the definition of AI, but once we see how the program works and understand the problem, we will not think of it as AIs anymore. Fortunately, I cannot identify a body technology that's unique to this field. Most of the work is problem specific. Okay. Some of the abstraction or creativity is required to see how to transfer. Okay. Interesting. And I'm seeing that the author is completely agreeing with this technique. Critique techniques for speech recognition, image recognition, are different from the expert systems. Hard time seeing how image recognition will be appreciable difference in programming practice. I'm seeing now expert systems, most advanced part of the AI art, and most widely applies technology for building expert system. And many of these software scientists are hard at work applying this technology into a software environment. Um, See now it's defined as an expert system is a program containing generalized inference engine and a rule base designed to take input data and assumptions, and explore the logical consequences. The inferences derivable from the rule base, yielding conclusions and advice, and offering to explain its results by retracing its reasoning for the user. Inference engines typically can deal with fuzzier probabilistic data and rules in addition to purely deterministic logic. So inference engines, application independent way, apply to many uses, and the changeable parts, code in the rule base of a uniform fashion in these, it's for developing, changing, testing, and documenting the rule base. And it regularizes the complexity. Interesting. Edward Feigenbaum. He's saying that power of systems not come from inference mechanisms, rather ever richer knowledge bases that reflect the real world more accurately. Okay. Now I want to see now how can this be applied to the software task, interface, rules, devising and testing strategies. Okay. So now we want to walk through this example. So imagine you're a testing advisor. Um, It's a pilot's checklist, okay, fundamentally offering suggestions as to possible causes of difficulty. So rule base is developed. Suggestion becomes more specific, taking on more specific, sophisticated account of the trouble symptoms reported. One can visualize a debugging assistant that offers a very generalized um, suggestions at first, but as more and more system structure is embodied in the rule base, as more and more particular in the hypotheses is generated in the test, it recommends. So work generate required to generate the diagnostic rules is work that will have to be done anywhere in generating test cases for the modules and for the system. General suitable general manner, uh, uniform structure for rules, and a good inference engine available. It may actually reduce total labor of generating, bring up test cases. Same way, postulate other advisors, probably many of them, and probably simple ones for the other parts of the software construction test. So main difficulties stand in the way. Crucial part of an imaginary scenario is development of easy ways to get from program structure specification to the automatic or semi-automatic generation of diagnostic rules. Even more difficult and important is the twofold task of knowledge acquisition. Okay. So finding experts who know why, okay, who know their why, and then also efficient techniques for extracting this information, distilling into the rule bases. Powerful contribution to expert systems will surely be to put at the service of the inexperienced programmer. Okay. Accumulated wisdom of the best programmers. Okay. No, and yeah, and this makes sense. It's not a very small contribution. And the gap between the best software engineering practices and the average is very wide still. Yeah. Perhaps wider than any other engineering discipline. So yeah, and I'm getting from this is it's just very important to have good practice within software engineering and that learning correctly is the best way to learn. Um, Moving on to automatic programming. So um, for almost 40 years, wow, okay. People have been anticipating in writing about automatic programming, generation of program for solving a problem for statement of the problem specifications. Some people today write as that this technology is to provide the next breakthrough. Okay. Oh, so this term is glamour and not semantic content. Okay. So in short, automatic programming has always been a euphemism for programming with a higher level language than was presently available to the programmer. So he's arguing that in most cases, it's the solution method, not the problem. Okay. So there's exceptions as well. Um, Technique of building generators very powerful, and very routine. So some systems for integrating differential equations have also permitted direct specification of the problem. System assess the parameters, chose from a library of methods of solution, generate the programs. These applications have very favorable properties. The applications oh, oh, have also permitted direct specification of the problem. Um, and these favorable properties, problems are readily characterized by few parameters, many known methods, and extensive analysis leading to these selected solution techniques, given these problem parameters. Hard to see how such techniques generalize to the wider world. Um, wow, okay. So there's graphical programming as well. So um, favorite subject for PhD dissertations. Wow, okay. Software engineering, graphical, so visual programming, computer graphics to software design. So it's with the analogy of VLSI chip design, where computer graphics plays so fruitful a role. Sometimes the approach is justified by considering flowcharts as the ideal program design medium, providing powerful facilities for constructing them. So in the first place, um, best viewed by Burks, the flowchart is a very poor abstraction software structure. Okay. And for their proposed computer in pitiful multi-page connection box form to which flowchart statement library proved to be essentially useless as a design tool. Programmers draw flowcharts after and not before writing programs they describe. Okay. Screens of today are too small and pixels show both the scope and the resolution of a seriously detailed software diagram. So-called desktop metaphor. Today's workstation is instead of airplane seat metaphor. Anyone who's shuffled a lap full of papers while seated in a coach between two portly passengers will recognize the difference. One can see only very few things at once. True desktop provides overview and a random access to score pages. Moreover, when fits of creativity run strong, more than one programmer or writer has been known to abandon the desktop for more spacious floors. So hardware technology will have to advance quite substantially before the scope of our scopes sufficient to the software design task. Whether we have diagram control flow, variable scope nesting, variable cross references, data flow, hierarchical data structure, whatever we feel. Only one dimension of the intricately interlocked software elephant. We superimpose all the diagrams generated by the many relevant views. It is difficult to extract any global overview. VLSI analogy is fundamentally misleading. Chip design is layered, two-dimensional object whose geometry reflects its essence. Software system is not. Okay. So it's important that hardware keeps on evolving as software continues to evolve, I see. Um, I want to move into program verification. Um, Much of modern programming, as I'm reading, goes into testing and repair of bugs. Okay. Is there a silver bullet to be found by eliminating errors at their source in the system design phase? Okay. Can both productivity and product reliability radically enhanced by following profoundly different strategy, proving designs correct before the immense effort is poured into implementing and testing them. So, um, there's no magic. Um, as I'm reading, program verification is a very powerful concept, and it will be very important for such things as secure operating system kernels. Technology does not promise, however, to save labor. Verifications are so much work that only a few substantial programs have ever been verified. Program verification does not mean error-proof programs. There's no magic here either. Mathematical proofs also can be faulty, whereas verification might reduce the program testing load. It cannot eliminate it. More seriously, even perfect programming verification can only establish that a program meets the specification. The hardest part of the software task is arriving at a complete and consistent specification. Much the essence of building a program is, in fact, the debugging of the specification. Okay. So like a program that's like easy to work, that easily works, doesn't run into a lot of problems because the design itself um, was was done correctly. Okay. Okay, so now this is elaborating on environmental tools. So, how much more can be expected from the exploding researches into better programming environments? One's this instinctive reaction is that the big payoff problems were the first tacked and have been solved. Hierarchical file systems, uniform file formats, as to have uniform program interfaces, and generalized tools. Language-specific smart editors are developments not yet widely used in practice, but the most they promise is freedom from syntactic errors and simple semantic errors. Perhaps the biggest gain yet to be realized in the programming environment is the use of integrated database systems. Keep track of the myriads of details that must be recalled accurately by the individual programmer and kept current in a group of collaborators on a single system. Surely this work is worthwhile. Surely it will bear some fruit in both productivity and reliability, but by its nature, the return from now must be marginal. Okay. Workstations. Gains are to be expected for the software art from certain rapid increase in the power of memory capacity of the individual workstation. How many MIPS can one use fruitfully? Composition of editing programs and documents is fully supported by today's speed. Compiling can set a boost, but a factor of 10 in machine speed would surely leave think time the dominant activity in the programmer's day. Indeed, it appears to be so now. More powerful workstation we surely welcome. Magical enhancements from them we cannot expect. Okay. So we expect change, but not like we can't expect it overnight. Okay, interesting. Promising attacks on the conceptual essence. So even though no technological breakthrough promises to give soft of magical results with which you're so familiar in the hardware area, there is so both an abundance of good working going on now and the promise is steady if unspectacular progress. All of the technological attacks on the accidents of the software process are fundamentally limited by productivity equation time of the task. So the sum of frequency times time. Okay. I as if as I believe the conceptual components of the task are now taking most of the time, then no amount of activity on the task components that are merely the expression of the concepts can give large productivity gains. Hence, we must consider those attacks that address the essence of the software problem, the formulation of these complex conceptual structures. Fortunately, some of these are very promising. The most radical possible solution for constructing software is not constructed at all. Every day, this becomes easier as more and more vendors offer more better software products for dizzying variety of applications. While we software engineers have layer and production methodology, personal computer revolution has created not one, but many mass markets for software. Every newsstand carried monthly magazines, which sorted by machine type, advertised, and reviewed dozens of products at prices from a few dollars to a few $100s. More specialized sources offer very powerful products for the workstation and other Unix markets. Even software tools and environments can be bought off the shelf. I've elsewhere proposed a marketplace for individual modules. Any such product is cheaper to buy than to build afresh. Okay. Even at a cost of 100,000, a purchase piece of software is costing only about as much as one programmer a year. And delivery is immediate. Immediate, at least for products that really exist. Products whose developers can refer the prospect to a happy user. Moreover, such products tend to be much better documented and somewhat better maintained than homegrown software. The development of the mass market is, I believe, the profound long run trend in software engineering. Cost of software has always been development costs, not replication costs. Sharing that cost among other few users radically cuts the per user cost. Another way of looking at it is that the use of n copies of a software system effectively multiplies the productivity of its developers by n. That is an enhancement of the productivity of the discipline and then of the nation. The key use issue, of course, is applicability. Can I use the available off-the-shelf package to my task? Surprising thing that has happened here during the 1950s and 60s studies showed that users would not use the package off-the-shelf packages for payroll, inventory control, accounts receivable, etc. Requirements too specialized, case-to-case variation too high. In the 1980s, we find such packages in high demand and widespread use. What has changed? Not only the packages, they may be somewhat more generalized and so much more customizable than formerly, but not as much. Not really the applications either, if any of the businesses and scientific needs of today are more diverse, more complicated than those 20 years ago. Okay, so they're more popular because the use case is able to apply to much more applications. People have a need for it. Okay, I'm saying now. Big change has been in software slash hardware cost ratio. Okay. Buyer of a 2 million machine in 1960 felt that he could not afford $250,000 more for a more customized payroll program. One that slipped easily and non-disruptively in the computer hostile social environment. Buyers of $50,000 office machines today cannot conceivably afford customized payroll programs, so they adapt their payroll procedures to the packages available. Computers are now so commonplace, if not yet so beloved, that the adaptations are accepted as a matter of course. There are dramatic exceptions to my argument in that the generalization of software packages has changed little over the years. Electronic spreadsheets and simple database systems. These two powerful tools, so obvious in retrospect and yet so late in appearing, lend themselves to myriad uses. Some quite unorthodox articles and even books now abound. How to tackle unexpected tasks with a spreadsheet. Large number of applications that would formerly have been written as custom programs, COBOL or report program generator, now routinely done with these tools. Generators are now okay. Many users now operate their own programs day to day, day in and day out, on varied applications that are writing program. Indeed, many of the users cannot write new programs for machines, but they're nevertheless adept at solving new problems with them. Single most powerful software productivity strategy for man organization is to quit the computer naive intellectual workers on the firing line with personal computers and good generalizing, writing, drawing, file and spreadsheet programs and turn them loose. Strange strategy, simple programming capabilities will also work for hundreds of laboratory scientists. So it's not about developing now. It's more of like, how do you use these software products? How do these products that people have made already improve life? Okay, interesting. Requirements refinement and rapid prototyping. Hardest single part of building a software system. Designing precisely what to build. No other part of the conceptual work is difficult as establishing detailed technical requirements, including all the interfaces to people, to machines, and to other software systems. No other part of the work so cripples the resulting system if done wrong. No other part is more difficult to rectify later. Therefore, the most important function that software builders do for their client is an iterative extraction and refinement of the product requirements. For the truth is, the clients do not know what they want. They usually do not know what questions must be answered, and they almost never thought of the problem in detail that must be specified. Even a simple answer make this new software system work like our old manual information processing system is in fact too simple. Clients never want Exactly that. Complex software systems are moreover things that act, that move, that work. The dynamics of that action are hard to imagine, so in planning any software activity is necessary to allow for an extensive iteration to the client and the designer as part of the system definition. I would go a step further and assert that it's possible for clients, even those working with software engineers, to specify completely, precisely, and correctly the exact requirements of modern software product before having built, tried some version of the product they're specifying. Okay, so therefore, one of the most promising current technological efforts, and one which attacks the essence, not the accidents of the software problem, is the development of approaches and tools for rapid prototyping the system, part of the iterative specification of requirements. Okay. Prototype software system is one that simulates the important interfaces and performs the main function of the intended system, while not necessarily bound by the same hardware speed, size, or cost constraints. So like an MVP, okay. Minimum viable product, okay. Prototypes typically perform the mainline tasks of the application but make no attempt to handle exceptions, respond correctly to invalid inputs, abort cleanly. The purpose of prototype is to make real the conceptual structure specified so that the client can test for consistency and usability. Much presentation software exposition procedures rest upon the assumption that one can specify a satisfactory system in advance, get bids for its construction, have it built and install it. I think this assumption is fundamentally wrong and that many software acquisition problems spring from that fallacy. Hence, they cannot be fixed without fundamental revision. One that provides for iterative development and specificating prototypes and products. Okay. Still remember the jolt I felt in 1958 when I first heard a friend talk about building a program as opposed to writing one. Okay. Flash be broadened my whole view of the software process. The metaphor shift was powerful and accurate. Today we understand how, like other building processes, the construction of software is, and we freely use other elements of the metaphor, such as specification, assembly, components, scaffolding. Building metaphor has outlived its usefulness. It's time to change again. If, as I believe, the conceptual structures we constructed are too complicated to accurately specify in advance, too complex to be built faultlessly, then we must take a radically different approach. Let's turn to nature and study complexity in living things instead of just the dead works of man. Here we find constructs whose complexities thrill us in awe, with awe. The brain alone is intricate beyond mapping, powerful beyond imitation, rich in diversity, self-protecting and self-renewing. The secret is that it is grown, not built. Okay. So it must be with our software system. Some years ago, Harlan Mills proposed that any software system should be grown by incremental development. Okay. Incremental development, prototyping built into that. Okay. That is, the system should be first be made to run, even though it does nothing useful except call for the proper set of dummy sub programs. Then bit by bit it's fleshed out with the sub programs in turn being developed into actions or calls to empty stubs in the level below. Seen the most dramatic results since I began urging this technique on the project builders in my software engineering laboratory class. Nothing in the past decade has so radically changed my own practice or its effectiveness. Okay. The approach that necessitates top-down design, for it is a top-down growing of the software. It allows easy backtracking. It lends itself to early prototypes. Each added function and new provision for more complex data and circumstances grown organically what is out there. So get something working. I'm seeing right now, what I'm learning is like build something that works and then continue to add as you talk to more users, there's more use cases that are needed for the software. So just have the idea and build out that idea that you are thinking of. I see. The moral effects are startling. Enthusiasm jumps where there's a running system, even a simple one. Efforts redouble when the first picture from a new graphics software system appears on the screen, even if it's only a rectangle. One always has at every stage in the process a working system. I find that teams can grow much more complex entities in 4 months than they can build. Same benefits can be realized on large projects as on my small ones. Great designer, central question of how to improve the software art centers is it always on people. We can get good designs following good practices and poor ones. Good design practices can be taught. Programmers are among the most intelligent part of the population, so they learn good practice. Thus, a major thrust in the United States is to promulgate good modern practice. New curricula, new literature, new organizations, such Software Engineering Institute all have come into being in order to raise the level of our practice from poor to good. It's entirely proper. Nevertheless, I do not believe we can make the next step upward in the same way. Whereas the difference between poor conceptual designs and good ones may lie in soundness of design method. Difference between good designs and great ones surely does not. Great designs come from great designers. Software construction is a creative process. Sound methodology can power and liberate the creative mind. It cannot inflame or inspire. The Drudge differences are not minor, it is rather Salieri and Mozart. Study after study shows that the very best designers produce structures that are faster, simpler, cleaner, and produce with much less effort. Differences between the gray and the average approach and order of magnitude. Okay. So it's not like you're not, so I'm reflecting now. It's not more about like who can do it best, but like rather how are you doing it best? Like it's also like who are you doing it best, but also like the way you're getting to be the best, like faster, smaller, simpler, and then like the functionality is just so clean. Okay. Retrospection shows that although many fine, useful software systems have been designed by committees and built by multi-part projects, those software systems that have excited, passionate fans are those that are products of one or more few designing great designers. Designing minds, great designers. Consider units, APL, Pascal, Modula, and the Smalltalk interface, even Fortran, in contrast with COBOL, PL, Algo, MVS 370. Okay. Who did it well? Who did it? Who did not do it? Okay. Hence, although I strongly support the technology transfer and curriculum development efforts now underway, I think the most important single effort we can do now is develop ways to grow great designers. Okay. People that do it fast, clean. Okay. So no software organization to conclude can organize this challenge. Good managers scarce, though they be are no scarcer than good designers. Great designers and great managers are both very rare. Most organizations spend considerable effort in finding and cultivating management prospects. I have known of none that spends equal effort in finding and developing the great designers upon whom the technical excellence of the products will ultimately depend. First proposal that each software organization must determine and proclaim that great designers are important as to its success as great managers are, and that they can be expected to be similarly nurtured and rewarded. Not only salary, but the perquisites of recognition, office, size, furnishings, personal technical equipment, travel funds, staff support must be fully equivalent. How to grow great designers. Space does not permit a lengthy discussion, but some steps are obvious. Systematically identify top designers as early as possible. The best are often not the most experienced. Assign a career mentor to be responsible for the development of the prospect and keep a careful career file. Devise and maintain a career development plan for each prospect, including carefully selected apprenticeships with top designers, episodes of advanced formal education, short courses, all interspersed with solid design and technical leadership. Provide opportunities for growing designers to interact with and stimulate with each other. And like as I reflect, as I conclude this article, is that it's important with software development. It's like having the idea, knowing how to design. And I'm seeing why designers are so important because not only like how the system works, but also how does the user perceive the system. So I found this article to be very, very insightful and happened to learn a lot. So it's been great.